Hello everyone, I'm Anshuman Acharya, a first-year PhD student at Max Planck Institute for Astrophysics. Today I'll be talking about a project that was recently published in a paper in MNRAS, on which I worked upon with Dr. Vikram Khaire. It is titled, How Robust Are the Inferred Density and Metallicity of the Circumgalactic Medium? So we know that the absorption spectra from a quasar gives us the column density of metals in the line of sight clouds. And from this, we can actually infer the physical parameters of the cloud in our line of sight, such as its density or metallicity, and from that, even its thickness. But for that, we need its ionization correction. For the ionization correction, we need the UV background that was irradiated on the cloud. But we cannot observe the UV background directly, and hence we have to synthesize it. But then there's an issue. Different UV background models are obtained if we have different input parameters. We have shown 9 different UV background models here. For example, Khaire and Xian in 2019 varied one parameter, which is the quasar emissivity, by varying the spectral energy distribution and got 7 different models. We also look into Pushwin et al. 2019's models, which are an updated version of Hart and Maddow 2012, and Fouché-Giger 2020, which is an updated version of the 2009 results. But despite all this variation, all of these models are physically viable. For example, here we show that the observations of photoionization rates agree pretty well with all of the models. Thus, in theory, we should be using all of these models when we are trying to interpret the column densities of the circumgalactic medium. But that's not always possible. And we would have to sometimes use one UV background model and somehow report the variation that would come because of the choice of the UV background model. And that's exactly what we try to do here. We provide quantification of this variation. So here's our approach. We simulated a cloud with uniform density and metallicity using Cloudy, and then we chose one random UV background model and irradiated it with it. And we made 2 different types of clouds. One was the photoionized absorber, and second was the warm-hot absorber. In the warm-hot absorber case, we take into consideration collisional ionization as well. So in each case, we get a set of observed column densities, which can act as our mock observations. Now, we run a grid over density and metallicity for all the different UV background models and try to best match our observed column density. This will give us a result of what the density and metallicity could be on the choice of our UV background model. As a sanity check, we use the same UV background model and try to re-obtain our input density and metallicity. And we get it pretty well, as shown here for the photoionized absorber and for the warm-hot absorber. Now we move on. In the photoionized absorber, we take 165 unique combinations of 5 ions each for each of the UV background chosen. Here we have shown one of those examples. And we note that we are able to recover the hydrogen density pretty well, but with the deviation from the UV background model, the spread increases. We see a similar behavior for metallicity as well. And we note that there's a large variation of prediction depending on your UV background model. There's a factor of 5 variation for metallicity and a factor of 3.7 variation for the hydrogen density. And we also check if there is any dependence on the choice of our true hydrogen density and metallicity, and we have shown it here. So we present that the maximum variation in predicted density and metallicity values can be quoted as an error due to the UV background model, as shown in these values. In the warm-hot absorber case, we note that the metallicity is quite well constrained, but there's something interesting happening with the hydrogen density. We note that there's a bimodality here. And on investigating further, we find that it is because of neon 8 ion, which if it is chosen, gives us less spread in value and a less deviation from the true value. But if we do not choose neon 8, we get the bimodality as seen here in cyan and also a greater spread. This was showcased as well in our results here, where we see a more deviation and a variation for hydrogen density if we do not take neon 8. So to conclude, we note large variation in metallicity and hydrogen density on using different UVB models, and thus suggest caution in interpreting the physical parameters of CGM clouds. Further, we note that we need better constraints of the UVB input parameters, especially those that determine its shape, such as the intrinsic acidity of quasars and at its ionizing energies. More details are there in the paper, which can be found on arXiv as well as on the February issue of MNRAS.